We define the set of complex numbers as the set of numbers a plus bi, where a and b are real numbers and I is the square root of -1. We usually denote complex numbers with the letter Z, so Z is a plus bi. And also a little bit of notation when we want to take the real part of Z, so real of Z, that's the number a, so we write it like that, real of Z is a, and then the imaginary part of our complex number Z is b. So that's a little bit of notation, but what I want to do now is to look at the algebraic structure of the set of complex numbers, so how we can do operations with the complex numbers and what are the properties that those operations have. We did play a little bit already with the powers of the number I. We saw that I squared is -1 by definition. Then we took I cubed to be I squared multiplied by I, so that's -I, and so on. So you can review that in the previous video if you want. But what we're going to look at now is how when do we say that two complex numbers are equal? So we say that complex numbers Z1 is equal to the complex number Z2, and this is if and only if, by definition, both the real part and the imaginary part of the complex numbers coincide. So the real part of the first of them is equal to the real part of the second of them. And at the same time, the same is true for the imaginary part. The imaginary part of the first one is equal to the imaginary part of the second one. So that's the first thing. How do we say that two complex numbers are equal? To sum complex numbers, we have the following definition. Let's say we are trying to sum a complex number a plus bi plus a complex number that I'll call c plus di. So this sum is going to give a new complex number. The real part is going to be the sum of the real parts, so a plus c, and the complex part, the imaginary part, is going to be b plus d, so the sum of the imaginary parts. So, for instance, if we wish to sum the complex number 2 plus 3i plus the complex number -1 minus I, we need to sum the real parts, so we need to do 2 plus -1. And then we need to sum the imaginary parts, so we need to do 3 plus, and we have also -1 over here. So this is going to give me the complex number 1 plus 2i. In order to multiply complex numbers, well, we could learn a bit complicated formula, or what I'm going to do over here with these numbers, a plus bi multiplied by c plus di, is to apply a distributive property. So I'm going to multiply a and c, and I'm going to multiply a and di, and then bi times c, and bi times di. Okay, what is this? First we're multiplying a and c, that's a real number, ac, no problem here. Then we have a imaginary number where we have AD plus BC. All of that is being multiplied by I. So these are the two middle terms we have over here. And then at the end, what we have is B multiplied by D multiplied by I squared. But we know that I squared is -1. So actually all of this is just minus BD. So we can write our multiplication as AC minus BD. This is the real part. Plus, and then for the imaginary part, we have AD plus BC multiplying I. And this comes from applying a distributed property, just thinking as I as a symbol, and then at the end rewriting it using the property that I squared is equal to -1. Let's see an example of how this multiplication works. So let me make up two complex numbers to multiply. 4 plus 2i is being multiplied by 3 minus I. We could apply the formula, but I'm not going to go around remembering the formula. So instead of that, we are applying the distributive property because that we know for sure. So we have 12. Then we know that the other product that is going to give me something real is going to be 2i multiplied by -i. So what we are doing here is 2 multiplied by -1 multiplied by I squared. I squared is -1, so this is going to be just +2. And then for the imaginary part, we are going to have 4 multiplying -i is going to be just the -4. And then 2i multiplied by 3 is going to give us 6i. So +6, all of these times I. So this is 14 plus 2i. The sum and the multiplication of complex numbers inherits many of the properties that the sum and multiplication of real numbers have. For instance, if we want to sum or multiply two complex numbers, it doesn't really matter in which order we do it. So we can say that C plus W is the same as W plus C, or C multiplied by W is the same as W multiplied by Z. So that's a commutative property both for the sum and the product of complex numbers. We also have the associative property. So we can say that it doesn't matter if we first sum two complex numbers W plus V and then we sum Z, or if we first associate Z and W to sum them and then we sum V. And the same holds when we are multiplying complex numbers. So we have the associative properties for both the product and the sum. We also have a distributed property of the product and the sum of complex numbers. So if we have a complex number Z multiplying, let's say, U plus V, that's the same as Z multiplying U plus Z multiplying V. We also have two very important numbers that are the 0 and the 1. So they are the neutral values for the sum and the product of complex numbers. So if we have a complex number Z and we sum the complex number 0 in the real part and 0 in the imaginary part, we get Z back. We can just write that 0 plus 0i is equal to 0. If we multiply the complex number Z by the complex number that is in fact a real number, 1 plus 0i, then we get back our complex number Z. And again, 1 plus 0i, we can just write this as 1. It's worth noticing that if I change the place of 0 and 1, so I write 0 plus 1i, actually what I'm writing here is our number I. And the last thing that I want to mention is that when we multiply a number Z with the 0, we actually get 0 back. So these are all properties we expect our new set of complex number to have. We finish this video by seeing some examples. So we have two complex numbers. We want to sum them, subtract them, and multiply them. So I think you should pause your video here and try to see if you can do this by yourself. Let's see if you got it correct. When we are trying to sum, we're going to sum the real part. So we are going to sum 4 and 7 together to get 11. And then the imaginary part. So -5 plus 8 to get 3i. If I'm subtracting over here, maybe I want to just rewrite this as the first complex number plus, and I'm going to change the signs in the second one, so -7 minus 8i. Now the sum of the real part is going to be -3, and the sum of the imaginary parts is going to be -13. So 3 minus 13i. When I multiply them, I'm going to multiply the real parts together. 4 times 7 is 28. And I know that I'm also going to get a real number by multiplying the two imaginary parts together. So it's going to be 5 times 8 times 8, which is 40 with a minus of minus 40, but then multiply by I squared, so plus 40. And then for the imaginary part, real times imaginary is going to give me 4 times 8, 32, and minus 5 times 7, that's minus 35. All that multiplied by I. So this is 68 minus 3i.